Hi, it's Gary and welcome back to the workshop. I'm hanging out with all these soundboards because we're going to talk about soundboard manipulation today. And I'm going to share with you the concept that I've found to be the most important in controlling the sound in my own guitars, and that is thinning a soundboard plate to the correct flexibility. In this video, I'm going to tell you three key things. The first is a method to directly measure the flexibility in your soundboards. The second is how to actually thin a solid top soundboard to the correct flexibility and use that method of measurement to monitor our soundboards as we go. And finally, I'm going to give you the actual flexibility measurements that I use in my own soundboards so that you'll have a reference point to use in your own building. Because I feel that without giving you those actual measurements, which are often very tightly held as secrets among luthiers, without those measurements, all of the conceptual and measurement methodology will actually be useless. So I hope that these numbers that I share with you will serve as reference points that you can use to develop your own building style. Then in the next video, episode 14, I'll show you some advanced techniques on how I build double top soundboards, which are quite a bit more specialized than a solid top. And achieving the flexibility in a double top construction is a lot more difficult than in a solid top. So in that video, I'll share with you the methodology that I use to control the flexibility in a double top. Now let me introduce two additional concepts. I've found that achieving the correct plate flexibility is far more important than your bracing pattern or even your stiffness of your braces. So that if you get the correct flexibility even before you start bracing, you are far down the path towards achieving a good sound. But if you get the flexibility wrong, let's say you make the plate too flexible, the sound of the resulting guitar probably will be too bass heavy, boomy, and just not very articulate. If you make the plate too stiff, then you might get an overly bright sounding guitar that is really highly treble oriented and lack warmth or richness in the lower end. The second concept that I've learned over the years is if you apply the same flexibility to different soundboards of different species, let's say spruce versus cedar, and you carried these two guitars to completion, they would sound remarkably similar so long as you did other treatments the same, such as the bracing. In a blind listening test, those guitars would be very difficult for the audience members to tell which is spruce and which is cedar. And this goes against conventional wisdom that cedar is warmer than spruce, which is often brighter. And that's because if we equalize everything with the same flexibilities, we gain consistency in the sound, even to the point that different species really don't matter as much as we often think they will. But what is different is more on a subtle level that probably only players are able to discern, and that's because the species manifest the differences in sound more on the cellular level in terms of dampening properties and speed of sound after the initial attack. I encourage you to review these previous episodes where I gradually built up the theory that led us up to this point. But enough concepts for now. Let's get to the workbench and get to work. Thickness measurements don't necessarily tell us anything about a soundboard's stiffness because, as we've talked about in previous episodes, different boards have different inherent stiffnesses. And it gets more complicated than that because they can have different ratios of stiffness in what we would consider the with grain direction and what we call the cross grain direction. So wouldn't it make more sense if we thin our tops according to a certain flexibility that we have already correlated to good sounding guitars in the past? And this is exactly what we're going to do in an iterative process that I'm going to show you, where we do a little bit of thinning and we measure the stiffness and then we slowly sneak up to a target stiffness or target flexibility. So what we're actually doing is getting to a property in flexibility and stiffness that is much more closer to what really counts, and that is the resonant properties of the board, which is directly related to its stiffness. So that when we're all done with the process, it really doesn't even matter what the thickness measurement ends up being, other than it might be useful to have that measurement so that in future top constructions we have a ballpark estimate of where that target flexibility will end up being. What I'm going to do now is a demonstration of how I would take a solid spruce top and thin it to a target flexibility. Now, as I explained, I usually build double tops, but I've built many solid top guitars. And I know that the target flexibility that we are after makes a really nice sounding solid top guitar. So I've prepared for demonstration this top, which is in raw form now, quite thick and quite stiff. And I've inlaid a rosette that's prefab. And even though this piece of spruce, which is a density of 0.40 grams per cubic centimeter, is not the best cosmetically, mechanically and acoustically it's quite good, so that if I took this all the way into a finished guitar, the guitar would sound quite nice. The way that we're going to measure flexibility is using a technique known as deflection. We'll hang the plate like a bridge over a span of uniform distance and measure how much it bends under a uniform weight. We'll measure that distance with a dial indicator. And we'll do this in two directions, in the with grain and cross grain directions. For deflection measurements, there's no universally accepted distance for the spans or their positions. Every builder, if they use deflection, will use a different system. But what's important is for you to use the same format every time you build a top, and to record your results and then refer back to them when you build a new top. I'm going to show you the positions, distances, and weights that I use for my classical guitar tops and give you the deflection measurements that I target. So if you decide to use a different format for your guitars, but you want to refer to my numbers, I would suggest that you recreate my format, try to achieve those flexibility targets, and then repeat the process on your format so that you now have a transposition of the numbers from my format to your format, and then you can move forward from there. Here's the rig that I designed for doing deflection measurements, and it's just a convenient way to get the span uniformly distanced. And I use a very generic dial indicator, which I attach to the workbench, and the probe of the indicator pops through the table of the rig, and then that will get pushed down by the soundboard when I place a weight on top of it. This rig also allows me to remove the slats and place them in a different orientation so that now I can measure the cross grain stiffness. I just want to show you that you don't need a fancy rig to get the exact same results. You can go into the corner of your workbench and place your dial indicator there and have a set of triangles to suspend your soundboard, and so long as your distances are the same, this will work great. And I've done it this way for many years. Now I'm going to tell you in more detail how I constructed this rig and then give you the dimensions of my plate, because that will actually determine how much flexibility you will have If you have a smaller plate, you'll have a stiffer plate and it won't deflect as much as, say, a larger plate that has a larger span. If you don't want to know the details of this particular rig and you want to use something simpler, just skip ahead to the next chapter. To attach the dial indicator to the bottom of the workbench, I have a small mortise here, and then I have a threaded insert that I can attach the indicator with a bolt. The board is 1/2 inch thick MDF, and I've cut grooves halfway into it with a table saw to accept these slats, which are aluminum, which you can buy at the hardware store. They're 1/8 inch thick and 1.5 inch tall. If you happen to cut the grooves too wide, you can fill them with tape. You just want to make sure that the slats fit snugly into the grooves so they don't wobble. For measuring the width grain deflection, I'm most interested in the flexibility of the plate below the upper transverse bar, such as from here to here. That's because above the upper transverse bar in a finished guitar, it's relatively stiff in here because you have the head block and the neck and the fingerboard. So I want to know what's happening between here and here. So for the width grain deflection measurement, I place a slat at the widest part of the upper bout, and at the other end, down here, I suspend it 10 millimeters from the inside of the tail edge of the top in its final form, which is the thin black line here. Notice that I add 4 millimeters of overhang when cutting out my tops. That overhang is shown in the bold black line. The position of the dial indicator is half the distance of this span. For the cross grain measurement, by definition, I place the slats, again, 10 millimeters from the inside of the widest parts of the upper and lower bouts. And here are the dimensions, including that of the soundboard for this setup. Now for the weights that I use, for the width grain direction, I use a 2-pound weight, which I preload with ibex plane that is 180 grams, and I'll explain what preloading means shortly when we take an actual measurement. For the cross grain direction, I use this 180 gram ibex plane, and I preload with the 30 gram ibex plane. Now if you don't have these weights, you could easily use a cup of sand or fishing weights that achieve the same weights. But right off the bat, you can see from these weights that the cross grain stiffness is always going to be much more flexible than in the long grain direction. All right, so let's get to measuring our soundboard and get to thinning it. We're all set to go now, and I've got the top plate prepared. I've got the rosette inlaid and leveled and perfectly smooth on this side because we'll be taking material off of the bottom side. And I'm going to be keeping score of the physical properties, the weight of the plate as well as its thickness, and then give you some tap tones. And the idea is that I don't want to just have deflection data, I want to have all these tactile pieces of information feeding into me so that I can educate myself of how it feels and sounds to go along with all the data that I'll be collecting. So right now, in the width grain direction, very stiff, and my experience tells me this is way too stiff to have for a good sounding guitar. And in the cross grain direction, still too stiff and rather heavy in the plate weight. And this is what it sounds like right now. So this is how the deflection measurement goes. The first dimension that I'll do is in the with grain direction. And I'm going to load the plate. And the first thing that I want to do is to preload with this 180 gram weight, and I'm going to put it just left of where the probe sits, which is right here. And preloading just puts the plate and has it seated firmly so that when we take the actual measurement, it's not giving us false readings because the plate is moving around. So with the plate preloaded, I'm going to zero my dial indicator, and I've marked the 0 point with the red mark so you can see it. Okay, with it zeroed, now I'm going to take the 2-pound weight and I'm going to put it parallel to the slats, and I'm going to load the plate gradually. I'm not going to drop it down abruptly. I'm going to actually just softly drop it, and you'll see the dial indicator move. And so the reading is 0.10, we'll call it 106 inches. And my dial indicator works in inches, but you could also convert to millimeters if you want. It doesn't really matter. And now I'm ready to do the cross grain direction. So I will reorient the slats. And the plate goes back in. And you'll notice that I even have some pins that help register the position of the plate. So like the other direction, I'm going to preload the plate, but I'm going to preload with this 30 gram weight. And I'm going to preload just to the right of where the probe sits underneath here. Then I'll zero the indicator, and we're ready to apply the load. And I'm going to load now with the 180 gram weight very smoothly again. And the reading is 0.116 inches. Apart from the fact that I already told you that by experience, flexing in this direction, the plate feels too stiff, I haven't told you yet what the target flexibilities that I'm after are. And so the numbers that we just took in this deflection measurement are a bit irrelevant unless you already had some experience with it. So here's the important part for this particular project. These are the numbers that I'm targeting. Here are the deflection targets that I use in the two axes. The targets were derived over time based on record keeping and correlations to good sounding guitars. They produce spruce and cedar guitars that have good balance across the range, with excellent clarity, richness, and volume, and players often comment that they have large tonal palettes. Let me mention that the pair of deflection targets are intended to be used with a 28-foot radius lower bout and pretty conventional fan bracing. I can interchangeably use the patterns shown here with similar results. And then keep in mind when you add the bridge, that will greatly increase the cross-grain stiffness of the top assembly. You'll notice that for each deflection target, I denote an acceptable range of 10% more or less flexible than the target. And spelling it out, the range would look like this. In my experience, I can still achieve the sound that I want within this range because I can fine-tune the bracing to compensate for any deviations. Alternatively, if I want a warmer, richer sound, I can use an average bracing treatment in conjunction with a plate thinned to the higher end of the deflection range. In other words, a more flexible plate. And then vice versa for a brighter, more forward sound. Even if you don't use these numbers, the take-home message is that there is great power in objective measurements such as deflection, even if you only keep your final two numbers when your plate is done, it gives you reference points to correlate to sound. You can then replicate the results or rationally move the sound based on these markers. Especially for newer builders, such techniques can give you a lot of awareness and confidence instead of feeling that you're swirling in a universe of undefined possibilities. And just to be clear, in this video, I'm giving you more numbers than you actually need to keep in order to give you a good feel of how things are changing. So you can see that we're still quite far away from the target flexibility. And what I need to do now is from the underside of the soundboard, I need to remove material. And I'm going to do that with the drum sander to keep everything level. Now, there are many ways that you could achieve this. You could use a hand plane, you could use a hand sander, you could use scrapers, but for the sake of ease, I'm going to use my drum sander. You could also take off material in different patterns, and it's often traditional that you could take material off of peripheries once you get to a certain center depth. But for my system, I'm going to take it straight across and keep a consistent thickness all the way across the plate. The flexibility of a plate can change dramatically just with a few light passes on the drum sander, and I've only taken off 0.1 millimeters on that last set of passes. And the idea is to sneak up very slowly towards your target deflection because you don't want to go past. So just to my feel, based on experience, it feels like in the with grain direction it's still too stiff, and getting pretty close in the cross grain direction. But this is what it sounds like on the tap. And you can compare to the previous time. And here it is again. So the pitch is dropping as the stiffness decreases and the plate thickness decreases. This is what we expected. But let's actually take the deflection measurement now. Looking at our scorecard, you can see that while we've made some progress in the with grain deflection, there's still a ways to go to reach the target. In the cross grain direction, we're almost at the target. We'll talk more about what needs to be done on the plate in a moment. But first, this is a fantastic opportunity to talk about the changes we observed in each of these categories, because even at this early stage, there's a lot to be learned about the behavior of plates. The first point is that the loss of stiffness is not linearly related to the loss of thickness. Here you can see that we decreased the thickness by 4%, but the stiffness decreased much more than 4%, actually 21%. It's not a linear relationship because there's a well-known engineering principle for rectangular objects that the change in stiffness is proportional to the new thickness to the third power. Let's see if this relationship holds for the with grain deflection we measured for a 4% decrease in plate thickness. In our example, a 4% decrease in thickness means that 96% remains, which is 0.96. And raising that to the third power is 0.88. That is, 88% of the original strength remains, or a loss of 12%. Now the 12% predicted versus the 21% we measured is different, but I'm not going to get too hung up on it since we're in the right ballpark given the variability of wood, the fact that the plate is not rectangular, and there's some experimental error in the method. But the concept is helpful to understand what's going on and not be surprised that you can get large changes in flexibility with small changes in thickness. Here are a couple rules of thumb to keep in mind when you're thinning things like plates and braces. In the first line, you can see that a 10% decrease in thickness is predicted to result in a 27% decrease in stiffness. And in the second line, 50% results in an 88% decrease. And I show here how I calculated this. Stop the video here if you want to take a look at that. Now, looking at the cross-grain direction, this relationship that we just calculated clearly doesn't hold true. In fact, the thickness decrease results in an even more drastic decrease in stiffness. So in this axis, we need to pay particular attention. Returning to our scorecard and looking at the weight change, relative to the stiffness change, the stiffness decreases much faster than the weight decreases. I've mentioned in previous episodes that this is the case for many operations where we thin or carve structures. And this is a really good example of that principle. And here's where this comes into play. Looking at this relationship that pitch is proportional to stiffness divided by weight, if the stiffness decrease is much larger than the weight decrease, the plate will be predisposed to support lower pitches, even though stiffness and weight have opposing effects on pitch. And this is exactly what we heard when the pitch dropped, because the stiffness change swamped out the weight change. Okay, with this mini physics lesson over, let's move on to the business of thinning our plate. I can see from the deflection at this point that the cross-grain stiffness is very close to our target. However, in the with-grain direction, we still have a ways to go. So I'm going to do a maneuver that will allow me to preferentially decrease the stiffness in this direction versus this direction. So what I'm going to do is take more material off of this tail end and not touch so much of the wing area. It's more important to get the stiffness and flexibility correct in this with grain direction. It's the direction that resists string tension. It also, I found, is more related to the overall tonal quality. Whereas in the cross-grain direction, since it's not getting pulled as far as string tension, we have a little more leeway as far as the flexibility there. The other thing is that it just may be that this particular piece of spruce has a high degree of stiffness relative to the cross grain, and it just may not be possible to get enough flexibility in this direction without getting maybe excessive amount in this direction, at least according to our target flexibilities. So if I have to introduce more flexibility than targeted in this cross grain direction, so be it. Here you can see my plan for how I'm going to reduce the plate thickness, which starts at a uniform 2.3 millimeters. And I'm going to use a palm sander that's fitted with 220 grit sandpaper, and I'm going to taper from 2.3 in the middle out to about 2.0 on the periphery. after doing that selective sanding in this width grain direction, it feels like we're approaching where we need to be, maybe still not there yet. And in the cross grain direction, probably we're there, but it could still tolerate a little more flexibility if need be. So let's take the sound test. And here's how it sounds now. You can hear the pitches going down relative to what we had in the prior step. And let's check out the deflection. So based on what I see in the deflection, it's still a little bit stiff in the width grain direction, so I'm going to continue in the pattern of taking away material in this lower bout area, and then also maybe take some away in this area just below where the second transverse bar will be, just around the waist area. And after that last sanding treatment, the flexibility in the width grain direction is very close to where we need to be. We've already arrived at the correct flexibility, or maybe beyond our target flexibility for the cross grain direction. But if it's beyond what our target was, well, it can still tolerate that. So here's how it sounds. And compare it to the previous step. Let's check out the deflection now. Based on these deflection numbers and what I feel in my hands, drawing upon my experience, also what I hear, in my experience, it's time to stop. And what I'm going to do is just measure the thicknesses, because they're non-uniform. I want to show you what the thicknesses look like, and then we'll come back and talk about what we have. All in all, I think this soundboard plate will end up making a really great sounding guitar. And you can see from the topographical map of thickness that I preserved a central area, kind of like a peninsula within the lower bout, the center of the lower bout, to give it additional stiffness where it's needed, where the bridge will be attached and be under the most stress because of the pull of the strings. Looking at the map and the thicknesses, I think you can get a false sense of what's really going on, where we proved by deflection that the overwhelming amount of stiffness runs in this direction, the width grain direction, which is good because that's the direction where the strings are pulling and stressing the most. And what's happening in the cross grain direction is less critical for the structural integrity of the top. So really I've found over the years that you can have a very loose amount of stiffness or a lot of flexibility in this cross grain direction and still get a really nice vibrant sound, because having a lot of mobility in that direction still allows the top to move, which gives you pumping of air and a lot of volume, and also gives you enough flexibility so that your resonances are low enough to give you richness. So in this type of exercise, I hope you've gained an appreciation of the relationship between the stiffness as it pertains to the thickness. We saw that stiffness drastically decreases as we thin the top, and so small changes in top thickness can give you a lot of flexibility really fast. So you have to be very careful that you don't thin too fast and monitor your flexibility as you go. And so in future videos, we're going to talk about adding bracing and adding doming during that bracing, which will actually build up the stiffness again, and then we will carve the braces to kind of fine-tune and adjust the stiffness as we need it to finally get the right resonances before we glue the top to the sides. And speaking of bracing, the bracing pattern that I'm going to show you in a future video actually has a cross-grain bar that runs across underneath the bridge. And that's a good opportunity for me to leave it a little bit stiffer to compensate for this unusually flexible cross-grain top. And it just goes to show you that not every set of top wood has the same ratio of stiffness in the with grain direction and the cross grain direction. And so we were able to detect that using not only our hands, but the deflection measurements and based on the experience that I've had with other tops. Now with a solid top, you do have the chance that even after you glue the top to the sides, you still can come to the outside of the soundboard and still thin in order to add some flexibility if needed. And so we'll talk about more of those fine points in future videos, but at least for now, you have a good sense of how a lot of the theory that we've talked about in previous videos relates. Well, there you have it. These methods have worked really well for me, and I noticed that when I started using them, the quality of my guitars and the control I had over them improved immensely, and I hope that it'll help you too, either directly or indirectly. And at minimum, I hope that it can bridge the gap between theory and practice and help you as you develop as a luthier. In the next video, I'll be really excited to share with you how I build double top guitars, which is really my strong point. And so I look forward to seeing you back in the workshop at that time.